Hi everyone, I'm Fuming Fu. Over the next 30 minutes, I'd like to share some work on incident control for multi-tenant telemetry storage. I want to be upfront, this is a folk study, not a finished platform. So I will try to be clear about what we actually show and what we don't. The motivation is something a lot of us have lived. A team does a careful capacity study, learns where the system falls over, writes it down, and then during a real incident at 3 in the morning, none of that offline work in the form everyone can act on. This talk is about one way to close that gap and about being honest about its limits. Let me start with the problem. When you do a capacity sweep, we learn frontier, a map of for a given number of tenants in the query mix, and how much concurrency is still safe before the tail collapses. That part isn't controversial. It's a good evidence. The gap is the format. It usually lives as a CSV, a chart of someone's memory, and during an incident, the on-call engineer doesn't need a chart. They need a concrete action in this state. Today, that's often improvised under pressure, which is understandable, but slow and easy to get around. So our proposal is fairly modest in concept. Treat that offline frontier as something you compile ahead of time into an executable, auditable runbook. We're not the first to argue for structured runbooks for offline capacity modeling, and we build on that work rather than replace it. Our claim is narrow. The compiler step itself, turning measured evidence into a deterministic, partially identified artifact, is worth doing, and that a few choices instead matter more than you would expect. The one-line version is that incident control should be compiled contract from measured evidence rather than thresholds invented mid-incident. This is a substantial line of work on online overload control, credit-based admission, bi-level throttling, and I see this as complementary, not competing. A compiled runbook could be the policy input such as a controller consumes, and what we add is the offline to online compiler, and that audit trail, which that work generally doesn't address. I will spend the rest of the talk on how we compile it, why a couple of seemingly minor choices turn out to be load-bearing, how we try to make the safety deploy, and just importantly, where the evidence is thin. Why not just set up a cap and move on? Three reasons, and none of them are new observations on their own, but together they shape the design. First, capacity isn't a fixed number. The safe operating point moves with tenant count, query mix, and the container CPUs and the memory budget. So the burst shape. So a single static threshold is usually wrong in one direction or the other. Second, this is the one I find most interesting, censoring. When the system is overloaded, request timeout, and a timeout is a right sensory observation. You know it took at least the timeout, but not how long it really would have taken. The trap is that if you compute your trail only over completed requests, which a lot of metrics quietly do, then as the system gets worse and more requests are cut off, you, a preserved tail, can actually look better. The metric improves while reality degrades. Third, global controls spill over. If you only lever is one cap for everyone, then protecting against having tenant also penalizes the small, well-behaved ones. To make that concrete, one tenant files an expensive query, global cap throttles everybody, and a dozen small tenants who did nothing wrong eat the latency. None of these are exotic. The point is just that meme-based alerts and one-shot global caps miss out three. So a useful guardrail has to be context-aware, sensor-aware, and tenant-aware. I also be honest that they three aren't equally weighted in our results. The sensor one turned out to be the most consequential in our setup, and I will come back to why. That's what we tried building, and I will be candid later, but where it's only partially validated. Here's the approach: a three-stage pipeline, and this diagram is most of the system. Stage A is offline. We run a capacity sweep, varying the engine, the tenant count, and the concurrency over several Cs, pushing until things break, and that gives us the frontier, the safe capacity boundary. The frontier is really all stage A produces. Stage B is the compare step, and its part we point to as the contribution. We take the frontier plus a frozen fairness policy, just a config file, and emit a single artifact, runbook.json, with the content hash. I would stress it's a structured executable strategy, not prose. It carries the zoom caps, the trigger thresholds, hysteresis, and the action ladder, plus metadata recording exactly which evidence produced it. Stage C is online. A small controller loops over 60 seconds windows, scores the situation, and applies the runbook escalation or backing off. An average stage writes one audit trail, commit, config, image digest, and the runbook hash. So the policy running in production is probably the one compiled from a given piece of evidence. Let me be measured about the claim. None of the three stages is individually novel. Sweeps, runbooks, and Windows controllers all exist. What we are arguing is that binding them with the content hash artifact, so evidence, policy, and execution are one auditable unit, is a useful discipline. Concretely, the compare is just arithmetic. Take the conservative frontier, subtract the margin to get a red cap, derive yellow and green by fixed ratios, and claim them so they stay ordered. Then attach the evidence metadata and hash. It's deliberately boring and deterministic, as you can rerun it and get a byte identical output, which is the point. One honest, practical note on stage A. The sweep is embarrassingly parallel, and you would run it per hardware tail, not per instance. So keep the current strip, but that's assume your hardware tiers are stable enough to sweep in the first place. For the runbook, two pieces. On the left, the zones, green, yellow, red, which adjusted score each 60-second window. Green means comfortably under the safe limit, yellow degrading, and red is failure. Each zone carries an admission cap derived from the conservative end of the frontier, and minimum across Cs with a margin, then space and clamp so they stay monotone. I will flag plainly that the exact cap values are heuristic. The ratios are frozen parameters, not something we claim is optimal. On the right, the action ladder. The idea is that admission control long isn't enough, because sometimes the problem is expensive queries, not too many of them. So there are four progressive steps: tighten admission, then the query window, then top K, and selective skip, and only at the top cap cardinality. The controller climbs one rung at a time, only as far as the zone demands and is bounded, and most first steps and 8 windows, then stops and heads back to a human. Then glue is hysteresis. It holds for 2 windows before relaxing, and only exits after 2 consecutive green windows, which keeps it from flapping. The one invariant we do enforce is that it never relaxes while risk is still worsening. There is also a minimum sample guard, so a couple of unlucky requests in a query window can trip into red. The runtime loop is equally boring on purpose. Each window it scores the zoom, climbs the step. If it's still yellow or red, comes toward exist and is back down after the heart if it's green. And either X after 2 green windows or give up after 8 and page is human. And I would be honest that a lot of these constants, the 2 window hold and the 8 window budget, the 0.8 spacing ratios are reasonable defaults with rows, not values we shown to be the best. What we have tested is that the structure as a whole behaves, that removing pieces hurts, which I will show in a minute. The next point is the one I would want you to take away, though I will try to not oversell it. Take the same overlord and score it in two ways. On the left, there's sensor blind way, which is honestly how a lot of systems do it. Compute the tail over completed requests and drop the timeouts because they don't have a latency number. As overlord worsens, more requests are dropped from the calculation. The survivors look fine. Our server P99 force, output looks near 1 and raises screen. In our runs, the controller scoring this will produce 0 escalations and 0 zoom flips across 24 incidents. It stayed silent through genuine overload because its own magic said everything was fine. On the right, the sensor aware version, we count timeouts, aborts, and over deadline requests as violations. And the good put denominator includes the sensor attempts. Now the violation weight rises. Good put drops. It scores red and it acts. Same instant, opposite verdict. Mechanically, that's the entire trick. The sensor blind version let its own denominator shrink as timeouts climb. So the number it watches improves, while the sensor aware version keeps those attempts in the denominator and counts them as violations. So it says what's actually happening. It's almost a one-line change in how you compute the metric, but it's the difference between acting and staying silent. I would be careful about how far to generalize it. Censoring is a textbook survivor analysis, so the idea isn't ours. Our contribution is just applying it here and showing concurrently that without it, the controller is inert. But I do think the practical lesson travels if you overload signals drop timeouts. They can mislead you exactly when it matters, and that's worth checking your own dashboards. One fairness note, we score on the worst affected tenant, the maximum across tenants rather than the average. So a single struggling tenant can't be hidden, but everyone else have the traffic. A controller that throttles automation skip works, and the caps cardinality is not something an operator should deploy on trust. So we tried to make it auditable rather than ask for trust. 3 things. First, the policy is frozen before the first experiment state. We locked config, compile, record everything that wrong with separate building the model from testing it. So we can quietly tune on our own outcomes. Second, the animation caps are monotone and collapsed with headroom taken from the measured boundary. So the compile limits are internally consistent rather than a pile of handset numbers. The phrase protocol itself is just discipline. Look the fairness config, compare every runbook, record the scope, the evidence, and hash, and only the round. Once the receipt has run, nothing about policy can change without leaving a new hash behind. Third, every runbook carries a SHA 256 hash binding those exact rows into a commit, a config, and an image. Change anything, and you get a new hash. So you can put a hash diff alert in front of a rollout and catch a stale or mismatched runbook before and the traffic shifts. The phrase cuts both ways. If you do need to change your policy later, that's a lot, but it forces a recompile and a new hash. So there's no silent drift. Let me be honest about what this does and doesn't buy you. Hashing and freezing give you traceability and reproducibility, which I think genuinely matter. But they don't by themselves prove the policy is correct. They make it auditable, and they make it hard to run something you didn't review. Correctness still rests on the evidence, so let me turn to that, including its gaps. So that's the work. How much should we read into it? The setup is a 48-paired instant replace, 2 engines, ClickHouse and timescale DB, 2 scenarios, a burst, and a sustained setup, 12 seed each, and every method runs the identical instant, so only the decision is logic differs. The compiled run book recovers in all 48. No action recovers 12. The 4 other baselines, a one-shot cap, a global clamp, a naive tail controller, and a delayed reactive scaling land between 29 and 34 of 48. I want to be fair to those baselines. They are reasonable models of common on-call practice. They recover most of the time, and they are not strawman. The honest framing is that compiled and bonded was the only one that recovered every time in its setup. Note that the others are bad. One quality versus no action. The medians are good put to like up to 0.674, worse than 10p99 down to 486 milliseconds. And the timeout rate down a little. These are paired with Wilcoxon text p at most like 5.9 times 10 to the minus 9. With bootstrap interval that excludes 0, the mechanism is worth a look because the engine behaves differently. Timescale DB has room in its zoom and the result at the red capping about 2 window. While the ClickHouse safe capacity is so low that all 3 caps collapse to the same value. So admission control alone does nothing and it recovers only by climbing the ladder. It's worth naming the baselines so they're concrete. No action writes it out. The rest of the cap applies one zoom mapped cap once. Global cap clamps everything to a single fixed cap. Naive tail is the sensor blind controller, and the reactive scale as a fixed delay, then caps. They're all one shot, which is the realistic part. On-call relay re-evaluates every single minute. And the collapsed caps case on ClickHouse matters precisely because it shows the emission gradient isn't always there. And when it isn't, the latter is what carries the run. A couple more numbers. Recovery takes about 59 seconds on average versus about 112 for reactive scaling. And the controller itself is cheap, about 5.5 microseconds at P99 per window. Now the caveat I'd rather say than have you ask. This is the batch replay study on one deployment profile, 2 CPU, 4 gigabytes, and 1 second P99 deadline and 30-second timeout. So 48 out of 48 is strong evidence for this setting. A result like 48 out of 48 should make you a little suspicious that one piece is doing all the work, so we took components out one at a time, 24 rounds each to see what actually matters. Remove hysteresis and the recovery drops to 16 out of 24. So the anti-oscillation is a decoration. It's the first order. Keep the zoom, but dropping the ladder. Admission only, and you get like 12 out of 24. It handles ClickHouse, but fears timescale DB completely. 0 out of 12. Good put around 5%. Because you can't fix expensive query overload by admitting fewer queries. The sensor blind variant we already saw, 0 escalation. It never wakes up. To be precise about that sensor blind row in dust log, 21 out of 24 formal recoveries, but those are passive. The transient bursts subside on their own. The controller itself never acts and timescale DB stays in red. So I wouldn't count it as the method actually working. If there is a failure in the other direction, what's being candid about too aggressive policy formally recovers 24 out of 24, but it over mitigates, driving timescale DB to about 9% good boot by skipping and capping too hard. So it passes the recovery bar while effectively taking the system down. That last one is a useful reminder that our own recovery metric can be satisfied by a bad policy, which is exactly why the real letter is conservative. I read this evaluation as evidence that each piece pulls within our setting. Remove any one break something specific rather than as a proof of our particular constants are optimal. One design choice deserves scrutiny because a reviewer will ask, which point on the frontier do we compare from? The frontier varies across cities, so you could take the minimum, the most conservative boundary, or something more loose like the median, which gives higher caps. Our default is the median. We tested the alternative directly. We compare with the median, seeing for some policy otherwise. In that 24 wrong sensitivity batch, the median recovers 21 out of 24 against 48 out of 48 for the conservative minimum in the main campaign, and the figures aren't random. They concentrate where it worry most. Timescale DB under sustained setup, failing 3 out of 6. Split by engine, the median caps leave ClickHouse fine, 12 out of 12. The concrete, the damage on timescale DB 9 out of 12. So it isn't a uniform regression. It's a specific safety loss under sustained load on engine that had more headroom to misuse. The reason is that the loser median caps admit loss. The the conservative cap would have been reused. So the system works into a sustained overload state. I can climb out of it. So there's a real trade-off. Median buys a little headrooms under short bursts and loses safety under sustained pressure. And for incident control, I'd rather be safe in the worst case, so we keep the minimum as the default. Let me put it together and be clear about what I think holds up. Three things. First, an offline frontier is real evidence, but it's inert during an incident until you compile it into something that executes. That compile step is the move we are advocating. Second, censoring is optional. If your overload signals drop timeouts, they can go quite exactly when you need them. So score timeouts as violations. That one is worth checking on your own systems, regardless of anything else there. Third, in our setting, conservative, bounded, and audit type behave better than global cap or a reactive outscaler. And it does so without wrecking the smart tenants. I would also stress this is meant to keep a human in the loop, not replace one. The bounded budget and the audit trail are there so an operator can review any escalation afterward and override the policy then when it's wrong. Thus, if any of the physical environment is what I call compile phrase, run from frontier, slice per release, compile some run book, freeze it, and put a hash diff alarm in front of a rollout. So what runs is always something you reviewed. Also, let me close honestly on the limits. This is a batch replay study, two engines, one hardware profile, so I can show you long horizon, false positive rates, or operator acceptance, and drift between sweeps. It's a real open risk. We manage with per release canary slice in that hash alarm. So at least 48 out of 48, we could take that as encouraged evidence under controlled conditions. And design principles comparatively don't drop timeouts. Stay conservative and auditable as the more portable part. I believe that's all the talk. Thank you. My email is on the slide, and welcome to any questions.